There is something happening right now, in the air between your eyes and this screen, in the space between one heartbeat and the next, in the stillness you mistake for emptiness inside the wall to your left. Something so consistent, so measurable, so rigorously documented, that it appears in the most peer-reviewed corners of modern physics, and almost nobody talks about it without selling something. That's the first strange thing. Not that the secret exists, but that every time someone tries to hand it to you, there's a price tag attached. A course, a method, a new identity to purchase, as if the structure of reality came with a subscription fee, as if the universe had been waiting for the right marketing team before it revealed itself. It hadn't. What quantum physics actually found, not the pop science version, not the metaphor dressed up as mechanism, not the version sold in weekend retreats, is stranger than what anyone is selling. And it is stranger in a very specific direction, not toward magic, not toward the idea that you can manifest a parking space by wanting it with sufficient emotional intensity. Stranger in the direction of you, toward the question of what you actually are and what reality actually means when the thing doing the observing is factored into the equation. Here is the paradox this entire video is built around. The universe, at its most fundamental level, does not behave the way your senses report. Every solid surface you have ever touched is almost entirely empty space. The sensation of solidity is an electromagnetic repulsion between electron clouds, not contact between anything truly solid. Every color you have ever seen is your brain's interpretation of a wavelength. The wavelength itself carries no color. Color exists entirely inside the nervous system, doing the interpreting. Every moment you have experienced as continuous, flowing, seamless reality is a construction, a very convincing one, assembled by a brain that receives fragmented, delayed, partial signals and renders them into the coherent story you call experience. Your senses were never designed for accuracy. They were designed for survival. And those are not the same project. A hawk sees ultraviolet light you cannot perceive. A dog lives inside a world defined primarily by scent frequencies you experience as nothing. A mantis shrimp has 16 types of color receptors. You have 3. The question is not whether these animals perceive more or less than you. The question is, if perception is this variable across species on the same planet, what exactly are we calling reality when we use that word? Whose version? Which frequency range? Which set of instruments? This matters beyond biology, because the same question, whose instruments, which range, is precisely the one quantum physics has been asking about the universe since the 1920s. And the answer it keeps arriving at is uncomfortable in a way that no amount of philosophical sophistication makes comfortable. The universe, at the smallest measurable scales, does not have a fixed, definite state independent of measurement. It is not hiding the answer. It does not have one until you look. That sentence deserves more than a quick read. We are going to spend the next several minutes building the scaffolding that lets you actually understand what it means, not as a slogan, not as a bumper sticker for the spiritually curious, but as a precise, documented, still unresolved feature of physical reality that the most rigorous science humanity has ever produced has been trying to digest for a century. So why does the universe hide itself from the people most capable of understanding it? That is the loop we are opening right now. We will not close it until the end, and I am telling you that deliberately, because the answer lives not in any single block of this conversation, but in what accumulates between them. One more thing before we go deeper. If you have spent time with ideas about quantum consciousness, the observer effect as a self-help principle, or the suggestion that intention shapes physical outcomes, I'm not asking you to abandon that. I'm asking you to set it down for a few minutes. Not because those ideas are necessarily wrong, but because you cannot see what is actually in a room if you are already holding a map that someone else drew of a different room. The real version of these ideas is more interesting than any borrowed version, and the price of accessing the real version is setting down what you think you already know. The real map. That's what this is. The rules you trust most are the ones most broken. Let's start with what you were taught. At some point in your education, middle school, high school, maybe a college physics class you half remember because it competed with other things that felt more urgent at the time, someone drew a diagram, an atom, a nucleus at the center, electrons orbiting it in neat circular paths like a miniature solar system rendered in chalk or ink. The image was clean, ordered, satisfying in the way all mechanistic images are satisfying. This causes that follows this. Everything has a position, everything obeys a rule. That image is wrong, not approximately wrong, not wrong in the peripheral details, while correct at the center. Structurally, foundationally wrong, wrong in a way that has been known since the 1920s, documented in thousands of experiments since then, and still has not fully reached the way most people think about the nature of the world they live inside. Here is what the diagram should have looked like. No neat orbits, no fixed positions. A blurry cloud of probability. Regions where an electron is more or less likely to be found if you measure it, but not actually located anywhere specific until the measurement happens. The electron does not travel from point to point, the way a planet moves between positions in space. It exists between measurements in a state of genuine indeterminacy, not because our instruments are too crude to detect its exact location, not because there is a hidden variable we haven't found yet, but because having a definite location, at that scale before the act of measurement, is simply not how nature operates. This is not a measurement problem. It is a reality problem, and that distinction is the sharpest edge in this entire conversation. For over 2 centuries, the dominant framework in Western science was what we call classical mechanics, the physics built on foundations laid by Isaac Newton in the late 1600s, refined and extended by generations of brilliant minds into something that looked by the late 1800s like a nearly complete description of physical reality. In the Newtonian picture, the universe is a machine, elegant, vast, intricate, but a machine. Every particle occupies a definite position at every moment. Every force has a definite origin. Every future state of the system can, in principle, be calculated from the present state, given sufficient information and computing power. Determinism all the way down. Cause produces effect. Effect traces back to cause. Clean, traceable, satisfying lines. It worked. For a very long time, it worked with astonishing precision. It calculated the paths of cannonballs and comets with equal accuracy. It predicted the return of Halley's Comet decades in advance. It built the engineering foundations of the Industrial Revolution. The model was so internally consistent, so reliably predictive, that by the 1890s, some prominent physicists were quietly suggesting that the foundational work of physics was essentially complete. The framework was in place, the equations were settled. What remained was refinement, not revolution. Then they looked more carefully at the details, and the details didn't cooperate. 3 separate experimental anomalies appeared, coming from completely unrelated directions, all pointing toward the same impossible conclusion. Blackbody radiation, the way heated objects emit light as a function of temperature, refused to follow classical predictions at high frequencies, producing what physicists called the ultraviolet catastrophe, a breakdown of the equations so severe that the classical model predicted infinite energy output, which is not a small discrepancy. The photoelectric effect, the way light shining on certain metal surfaces ejects electrons, produced results that had no classical explanation. The energy of the ejected electrons depended on the frequency of the light, not its intensity, which made no sense in a wave model where more intense light should mean more energy transferred. And atomic spectra, the specific colors of light emitted by different elements when energized, appeared not as smooth, continuous rainbows, but as sharp, discrete lines, specific to each element, as if atoms were only allowed to emit energy at exact, predetermined frequencies and nothing in between. 1 anomaly is a puzzle. 2 anomalies are a pattern. 3 anomalies from 3 different directions is a crisis, not a dramatic crisis, not the kind with raised voices and overturned certainties. The quieter kind, the kind where extremely careful, extremely serious people look at their data for months and realize that reality is not cooperating with the theory, that the theory, however beautiful, however functional at larger scales, is telling a story about nature that nature itself is contradicting at the smallest scales. Max Planck cracked the blackbody problem in 1900, but he cracked it in a way that disturbed him for the rest of his life. His solution required assuming that energy is not continuous, not a smooth flowing river that can take any value, but discrete, packaged into specific indivisible units he called quanta, from the Latin word for how much. He introduced this assumption reluctantly, describing it later as an act of desperation, a mathematical trick, a computational convenience he hoped someone would eventually replace with a cleaner solution that preserved the classical picture. Nobody did, because Einstein used the same discreteness to explain the photoelectric effect in 1905 and won the Nobel Prize for it, not, as many people assume, for relativity. And Niels Bohr used quantum ideas to model the hydrogen atom in 1913. And each time a physicist reached for the quantum as a temporary patch, it turned out to be load-bearing wall, not a bridge back to classical physics, a door into something structurally different. Here is what I want you to hold for a moment. The people who built quantum mechanics were not mystics. They were not romantics with a philosophical attachment to mystery. Planck, Bohr, Heisenberg, Schrödinger, Dirac, Pauli. These were among the most mathematically rigorous scientists of their century, and in many cases they deeply personally wanted the classical picture to survive. Werner Heisenberg, who developed the uncertainty principle, the principle stating that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa, not because of instrumental limitations, but because nature imposes this as a fundamental constraint, reportedly spent the night, he fully grasped the implications of his own mathematics sitting by the sea, unable to sleep, shaken by what his equations were telling him about the nature of reality. Erwin Schrödinger, who developed the wave equation that became the mathematical backbone of quantum mechanics, invented his famous cat thought experiment not as a celebration of quantum strangeness, but as a weapon against it, a reductio ad absurdum, a demonstration of what he believed was an absurd consequence of quantum logic taken seriously at the macroscopic level. If a quantum particle can be in two states simultaneously until measured, and if that particle is connected to a mechanism that kills a cat, then the cat must be simultaneously alive and dead until someone opens the box. Schrödinger intended this as a proof that something was wrong with the interpretation. The interpretation survived. The cat stayed in superposition. And this is the philosophical wound that has not fully healed in a century of trying. Because what quantum mechanics gave science is not simply a new set of equations for predicting experimental outcomes. It gave physics a new and deeply uncomfortable set of questions about what equations are actually for. Are they describing reality as it exists independently of us? Or are they only predicting the outcomes of measurements, outcomes that require an observer, an instrument, an interaction, and saying nothing reliable about what exists in between? In the classical picture, that question barely mattered. The equation described the cannonball's arc, the cannonball followed the arc, the target was hit or missed, and the entire chain was in principle observable at every step. Description and prediction coincided so completely that asking whether the equation was about reality, or merely useful for reality, seemed like a question for philosophers with too much free time. In the quantum picture, description and prediction split apart, and the crack between them is exactly where this video lives. Science solved the large, and in doing so, exposed how broken the small had always been. The experiment that changed physics also changed what you means. In 1801, a British polymath named Thomas Young performed what would eventually be recognized as one of the most consequential experiments in the history of human knowledge. He called it, without any particular drama, the double-slit experiment. At the time, it was designed to settle a long-running debate about the nature of light, specifically whether light was made of particles, as Newton had argued, or waves, as Young suspected. The setup was almost insultingly simple: a light source, a barrier with two narrow slits cut into it, a screen on the other side to catch whatever passed through. If light were particles, tiny bullets fired in straight lines, you would expect to see two bright bands on the screen, one directly behind each slit. Clean, direct, logical. The geometry of it practically demands that outcome. What Young saw was an interference pattern, dozens of alternating bright and dark bands spreading across the screen in the unmistakable signature of waves overlapping. Two waves emerging from two slits, meeting on the other side and either reinforcing each other where their peaks coincide, or cancelling each other where a peak meets a trough. It was beautiful, it was clear, and it seemed to settle the question definitively. Light was a wave, settled. Except that a century later, Einstein's explanation of the photoelectric effect proved that light also behaves as discrete particles, packets of energy called photons. And here the story stops being a debate between two clean options and becomes something that has no clean resolution. Because when physicists took Young's double-slit setup and fired photons through it one at a time, one particle, one event, one moment, the interference pattern still appeared, slowly, shot by shot, dot by dot, on the detection screen. But over thousands of individual photon detections, the pattern that emerged was not two bands, it was the full interference pattern. As if each individual photon, with no other photon present to interfere with, had somehow passed through both slits simultaneously, interfered with its own possible paths, and only resolved into a single impact point upon arrival at the screen. Think carefully about what that requires. A single particle traveling alone, producing the mathematical signature of two waves interfering. The only coherent explanation, the one quantum mechanics actually provides, is that before detection, the photon does not have a single definite path. It exists in superposition across all possible paths simultaneously. It is not secretly taking one path while we fail to detect which one. It is genuinely, physically, taking all paths at once, and those paths interfere with each other the way waves interfere, until the moment of detection collapses the whole probability structure into a single outcome. Superposition, not a metaphor, not a philosophical position, a measured, repeatable, experimentally confirmed feature of how physical reality behaves at the quantum scale. But then, the physicists added a detector. They placed a measuring device at the slits, something capable of registering which slit each photon actually passed through. The detector didn't block the photons. It didn't interfere with them physically in any dramatic way. It simply gathered information about which path each photon took. The interference pattern disappeared, completely. The moment the detector was active and capable of recording which path information, the photons stopped producing an interference pattern and started producing exactly the two-band pattern you would expect from classical particles. Turn the detector off, interference pattern returns. Turn it on, it vanishes. The photons somehow behave differently, depending on whether the universe contains a record of which path they took. The act of observation changed the physical behavior of the particle. Not theoretically, not philosophically, physically, measurably, reproducibly. This is the observer effect, and it is one of the most precisely documented and least honestly discussed findings in all of science. Because what it implies is not comfortable. It implies that the state of a physical system is not entirely independent of whether that system is being measured. That the act of extracting information from the universe, the act of looking in the most rigorous physical sense, participates in determining what is found. Now, before we go further, I want to address the objection forming in your mind right now, because it is a good objection and it deserves a direct answer. The objection is this: maybe the detector is physically disturbing the photon. Maybe this is not really about observation or information. Maybe it is just a mechanical interaction, the instrument bumping into the particle and changing its trajectory. Maybe there is nothing mysterious here at all, just clumsy instruments. That objection was taken seriously. It was tested rigorously, and the results came back in a way that made the objection harder to sustain, not easier. In the 1970s and 1980s, physicists developed what are called delayed choice experiments, building on a thought experiment proposed by John Archibald Wheeler, one of the most careful and respected theoretical physicists of the 20th century, a man not given to careless speculation. Wheeler's setup was elegant and brutal in equal measure. The idea was to wait until after the photon had already passed through the slits before deciding whether to measure which path it took. If the disturbance explanation were correct, if the detector were simply nudging the particle at the moment of passage, then deciding to measure after the passage should change nothing. The particle would already have committed to its path. It hadn't. The delayed choice experiments, refined and confirmed across multiple laboratories over several decades, showed that the choice to measure, made after the photon had already passed the slits, retroactively determined whether the photon had behaved as a wave or a particle. The present choice appeared to influence the past behavior, not the future, the past. Wheeler described this as the universe being, in some sense, participatory. Not in a mystical sense, he was allergic to mysticism, but in a precise physical sense, that the act of registering information about a quantum event is not separate from the event. That observation and reality are not two separate processes with one passively recording the other. They are, at the quantum level, entangled in a way that has no classical analog and no fully satisfying philosophical resolution. But the double-slit experiment and the observer effect are only half of what needs to be said here. The other half is entanglement. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper designed, like Schrödinger's cat, as an attack on quantum mechanics rather than a celebration of it. They described a scenario, now known as the EPR paradox from their initials, in which two particles interact and then separate. Quantum mechanics predicts that after the interaction, the two particles share a single quantum state. Measure one particle, and you instantly determine certain properties of the other, regardless of the distance between them. The correlation is immediate. Not fast, not very fast. Immediate, with no signal traveling between them. Einstein found this unacceptable. He called it spooky action at a distance, spukhafte Fernwirkung in German, and argued that it proved quantum mechanics was incomplete, that there must be hidden variables, local properties carried by each particle from the moment of their separation, that predetermine the measurement outcomes. The correlation isn't mysterious, he argued. It is simply information the particles were already carrying, like a pair of gloves separated into two boxes. Open one box, find a left glove, and you instantly know the other box contains a right glove. No mystery, no connection, just pre-existing information. It was a compelling argument. It was wrong. In 1964, physicist John Bell derived a mathematical theorem, now called Bell's theorem, that showed it is possible to design experiments that distinguish between Einstein's hidden variable explanation and genuine quantum entanglement. The two explanations make different statistical predictions about measurement outcomes when the detectors are set at different angles. If the correlations exceed a certain threshold, now called Bell's inequality, then local hidden variables cannot explain them. Only genuine non-local entanglement can. In 1972, John Clauser performed the first experimental test. The correlations violated Bell's inequality. Subsequent experiments by Alain Aspect in the 1980s, with more rigorous controls, confirmed the violation. Experiments by Anton Zeilinger and others across the following decades closed loophole after loophole that skeptics had identified. In 2022, Clauser, Aspect, and Zeilinger were awarded the Nobel Prize in Physics specifically for this work, for experimentally proving that the universe contains correlations that cannot be explained by any local hidden variable theory. Einstein's gloves analogy was not just incomplete, it was ruled out by experiment. The particles are not carrying pre-existing information. The correlation between them is real, immediate, and operates independently of the distance separating them. Two entangled particles on opposite sides of the planet, or in principle, opposite sides of the galaxy, remain connected in a way that has no mechanism in classical physics. Measure one, and the other responds. Not because a signal traveled between them, because they never fully became separate things. Non-locality is the technical term, meaning that the universe at the quantum level does not respect the assumption that things separated in space are truly independent of each other. Locality, the idea that objects are only directly influenced by their immediate surroundings, that causes and effects require a chain of contact traveling at finite speed through space. This assumption, which underlies almost every intuitive model of how reality works, is experimentally violated, not philosophically questioned, experimentally violated with Nobel Prize-level certainty. Let that land for a moment. The universe does not behave locally. Separation in space does not guarantee independence. Two things that were once connected can remain correlated in ways that transcend the distance between them, in ways that no signal, no hidden message, no preloaded information can account for. The connection is not mediated by anything traveling through space. It is prior to space in some sense that physics can measure, but not yet fully explain. And now we have three things on the table simultaneously. Superposition, particles existing in multiple states at once until measured. The observer effect, measurement participating in determining what is found, rather than simply recording what was already there. Non-locality, correlations between separated systems that cannot be explained by any local mechanism. Three features of physical reality, each individually strange, each independently confirmed by rigorous experiment, each pointing in the same direction, toward the conclusion that the classical picture of reality, discrete objects, fixed properties, local causes, passive observers, is not a simplified version of something more complete. It is a fundamentally different kind of story, one that works at the scale your nervous system evolved to navigate and fails at the scale where the actual constituents of that nervous system operate. Here is the question that opens the next section. If particles do not have definite properties until measured, and if measurement requires an observer, then what exactly is an observer? Physics can describe what measurement does to a quantum system with extraordinary mathematical precision. What it has never fully resolved is what measurement is what counts as an observation, whether the observer needs to be conscious, whether consciousness is even a coherent category within a physical description of the universe. Observation creates. But the observer has not been defined, and that unresolved definition is not a footnote in quantum mechanics. It is the central unresolved problem, the thing physicists and philosophers have been arguing about for a century without consensus, and the thing that connects the most rigorous science in human history to the oldest questions human beings have ever asked about the nature of their own existence. You have been collapsing possibilities without knowing it. Step back from the laboratory for a moment. Not because the laboratory is done, we will return to it in the next section with something even stranger, but because there is a kind of understanding that only becomes available when you bring what you have just learned into contact with the life you are actually living. Not as metaphor, not as inspiration, as structural parallel, a pattern that appears at the quantum scale and reappears in a different register at the scale of a human life. Here is the parallel. Before you measure a quantum particle, it exists in superposition. A cloud of possibilities, none of them actual, all of them potential. The full probability distribution of what it could become when the moment of interaction arrives. The wave function, as physicists call it, contains all possible outcomes simultaneously. No single outcome is selected. No path is taken. The particle is, in the most literal physical sense, undecided. Then measurement happens, and the wave function collapses. One possibility becomes actual. The others do not disappear. In some interpretations of quantum mechanics, they branch into parallel realities. In others, they simply become inaccessible. But from the perspective of this measurement, in this moment, one outcome is real and the rest are not. Now consider a different kind of wave function, the set of things you could have become by this point in your life. The careers not taken, the relationships not pursued, the beliefs not examined, the capacities never developed, because the conditions that would have activated them never arose, or arose and went unrecognized. This is not a lament, it is a structural observation. At every moment of your life, you have been a probability distribution of possible selves, and the accumulated weight of choices, circumstances, encounters, and interpretations has been collapsing that distribution, selecting one actuality from an enormous range of potentials. Not randomly, the collapse has been shaped by everything you brought to each moment, but also not with full awareness of what was being collapsed, what was being foreclosed, what possibilities were quietly becoming inaccessible while your attention was directed elsewhere. You have been collapsing a wave function your entire life. You just didn't have that language for it. And here is where I want to be precise, because this is the point where the idea most often gets distorted into something it isn't. The quantum parallel does not mean that positive thinking collapses reality into favorable outcomes. It does not mean that visualization replaces action, or that the universe is a wish fulfillment machine awaiting your emotional input. Those versions of the idea are not derived from quantum mechanics. They are borrowed from quantum mechanics, stripped of their mathematical content, and retrofitted onto a pre-existing belief system about how personal reality works. That is not what I am pointing at. What I am pointing at is more subtle and, I would argue, more useful. The act of observation, in the quantum sense, is not passive. It is participatory. The observer does not stand outside the system, watching it from a distance, recording what was already true. The observer interacts with the system, and that interaction is part of what produces the outcome. This is not a metaphor for attitude or intention. It is a description of how information extraction from a physical system actually works at the fundamental level. Now scale that up, carefully, without overclaiming, to the level of human perception and attention. What you attend to, you interact with. What you interact with, you change and are changed by. The psychologist William James, writing in the late 1800s before quantum mechanics existed, observed that the faculty of voluntarily bringing back a wandering attention over and over again is the very root of judgment, character, and will. He was not talking about physics. He was talking about the structure of human experience. But the structural logic is recognizable. Where attention lands, something happens that would not have happened in its absence. You are not a passive recorder of a fixed external world. You never were. The version of events you experience is assembled by a brain that selects, filters, predicts, and constructs. Neuroscientists call this predictive processing. The brain does not simply receive sensory input and report it faithfully. It generates a model of what it expects to perceive, compares incoming signals against that model, and updates only when the discrepancy is large enough to force revision. Most of what you experience as direct perception is actually prediction. The world you see is mostly your brain's best guess, corrected at the margins by sensory data. This means the model you carry, the assumptions, the categories, the emotional weightings, the narrative frames, is not a neutral container for experience. It is a participant in producing experience. Change the model, and the same external signals generate a different experience. Not because the external world changed, because the instrument doing the perceiving changed. That is not quantum mysticism. That is neuroscience corroborating to, at a completely different scale, the same structural principle that quantum mechanics discovered at the subatomic scale. The observer is not separate from the observed. The act of looking is not separate from what is found. Where does this become personally uncomfortable? Here. If the instrument shapes the reading, then the unexamined instrument produces unexamined readings. If the brain's predictive model is built from experiences and conclusions drawn in earlier, more constrained periods of your life, childhood, adolescence, early adulthood, periods of stress or trauma or simple inexperience, then you may be generating a highly sophisticated, highly detailed, deeply convincing experience of a world that is partially a historical artifact, not a lie, but a model that was built for a different set of circumstances and has been running mostly unrevised ever since. Not real the way the wall is real, not false the way a dream is false. Something in between, which is precisely the same category problem that quantum mechanics runs into with the wave function. And here is the application that actually matters, stripped of any self-help framing. The question is not how to think more positively. The question is how to become more accurate. How to hold the predictive model loosely enough that new information, genuinely new information, not just confirmation of existing categories, can actually register. How to remain, in some functional sense, open to outcomes that your current model does not predict and therefore tends not to notice even when they are present. That is a discipline, not a technique, not a practice you can complete in a weekend. A discipline in the classical sense, a sustained, ongoing commitment to revising the instrument you use to encounter the world, because the instrument is always partly wrong, because experience always exceeds the categories you bring to it, because the wave function of what your life could become is always larger than the slice of it your current model allows you to see. There is something specific about this that applies to people at a certain point in a life, and I am going to name it directly because I think you recognize it. There is a particular kind of narrowing that happens, not from failure, but from accumulation. You accumulate evidence, you accumulate experience. You accumulate a working knowledge of how things tend to go, what usually happens, what people are generally like, what you are generally capable of, where effort tends to pay off, and where it tends not to. This accumulation is valuable. It is the distilled product of years of actual contact with reality. It would be foolish to discard it. But accumulation without examination becomes calcification. The model that was built from genuine experience begins to function as a closed system, one that processes new input in terms of existing categories so efficiently that genuinely novel information gets quietly filed under something familiar and loses its novelty before it can do anything useful. You stop being surprised, not because the world has stopped offering surprises, because the instrument has become too good at converting the unfamiliar into versions of the familiar. This is not a character flaw. It is a structural feature of how sophisticated predictive systems work, and quantum mechanics, strangely, offers a kind of permission here. Not a solution, a permission. The universe itself, at its most fundamental level, does not foreclose possibilities until the moment of interaction. It runs on superposition, on the maintenance of multiple potential states simultaneously, right up until the instant that measurement forces a resolution. The tendency to foreclose early, to decide in advance what something is before fully encountering it, is not a feature of physical reality. It is a feature of the model. The model can be revised, not easily, not quickly, not by wanting it to be revised, but through the kind of sustained, honest attention that treats experience as genuinely open rather than pre-categorized. Through the practice, and it is a practice, not an insight, of catching the moment when the brain begins converting the unfamiliar into the familiar and pausing there. Not forcing an alternative interpretation, just pausing. Staying with the unresolved state a little longer than is comfortable. Physicists have a word for the capacity to hold multiple possible states without collapsing them prematurely. They call it maintaining coherence. And coherence in quantum systems is extraordinarily fragile. The slightest interaction with the environment, a vibration, a stray photon, any exchange of information with the surrounding world, causes decoherence, the rapid collapse of superposition into a single classical state. Maintaining quantum coherence requires extraordinary isolation from environmental interference. The parallel is imperfect but worth noting. Maintaining human coherence, the capacity to remain genuinely open to multiple interpretations of a situation before settling into one, is also fragile. It also collapses under pressure. Under time pressure, social pressure, emotional pressure, the pressure of a brain evolved to resolve ambiguity as quickly as possible, because ambiguity was costly in the environments where the human nervous system was shaped. The collapse happens fast, mostly below awareness, and produces a certainty that feels like perception, but is partly construction. Awareness changes this, but not in the way self-help sold you, not through a single realization that rewires everything. Through the slower, less dramatic, more durable process of repeatedly noticing the collapse as it happens, the moment when possibility narrows into conclusion, and occasionally, not always, not forcibly, but occasionally, choosing to stay in the superposition a little longer. That is where the quantum principle actually lives in a human life, not in manifestation, in attention, not in what you intend to happen, in how long you can remain genuinely uncertain before reaching for the resolution your model already has waiting. The universe runs on superposition until measurement forces a choice. You have more choice about when to measure than you think. The universe doesn't compute you, it might be you. We have been building towards something. Everything in the previous sections, superposition, the observer effect, entanglement, non-locality, the participatory nature of measurement, the way the instrument shapes the reading, has been scaffolding for a question that physics itself has not answered. A question that sits at the exact boundary between the most rigorous science humanity has produced and the oldest inquiry human beings have ever pursued. The question is this: what is the observer? Not who, what. Quantum mechanics requires an observer to complete its description of reality. The wave function evolves according to Schrödinger's equation, beautifully, deterministically, with perfect mathematical precision, until measurement occurs. At the moment of measurement, the wave function collapses. One possibility becomes actual, but the equation itself says nothing about what constitutes a measurement, nothing about what qualifies as an observer. The mathematics is silent on the one thing the mathematics cannot function without. This is not a minor gap. It is the central unresolved problem in the foundations of physics, and it has generated more serious philosophical disagreement among serious physicists than any other question in the history of the discipline. Not disagreement about the predictions. Quantum mechanics predicts experimental outcomes with a precision unmatched by any other scientific theory in history, accurate to more decimal places than any other physical theory ever formulated. The disagreement is about what the theory means, about what is actually happening when the wave function collapses, about whether the collapse is real or apparent, or whether the question itself is malformed. The interpretations are multiple, and each one is stranger than it first appears. The Copenhagen interpretation, the oldest and still the most widely taught, essentially brackets the question. It says, the wave function is a tool for predicting measurement outcomes. What happens between measurements is not a question physics should try to answer. Don't ask what the particle is doing when no one is looking. There is no fact of the matter. Measure, predict, verify. Stop there. This is sometimes called the shut up and calculate interpretation, a phrase attributed, probably apocryphally, to Richard Feynman, though it captures a genuine pragmatic strain in how quantum mechanics is actually practiced by working physicists. It works. As a practical framework, it works extraordinarily well, but it works by refusing to answer the question rather than answering it. And for anyone who finds the question genuinely interesting, which should be everyone given what is at stake, this is less a solution than a very elegant way of changing the subject. The many worlds interpretation, developed by Hugh Everett in 1957, takes the opposite approach. It refuses to bracket the question, and instead takes the mathematics with complete literal seriousness. The wave function never actually collapses, Everett argued. What we experience as collapse is simply what it feels like to be one branch of a continuously branching universal wave function. Every quantum measurement causes the universe to split. Every possibility is realized in a separate branch simultaneously. There is a branch where this photon went left and a branch where it went right, and both branches are equally real, and observers in each branch experience only their own outcome and have no access to the others. The many worlds interpretation preserves the mathematical elegance of quantum mechanics completely. It requires no collapse mechanism, no special role for observers, no mysterious boundary between quantum and classical. What it requires instead is an almost incomprehensible proliferation of parallel realities, a universe that is constantly, at every quantum event, everywhere, branching into copies of itself in numbers that make the total count of atoms in the observable universe look modest. Strange enough, there is more. The pilot wave theory, developed by Louis de Broglie and extended by David Bohm, proposes that particles do have definite positions at all times. Einstein's intuition was right about that, but they are guided by a real physical wave that propagates through all of space simultaneously and is sensitive to the entire experimental arrangement instantaneously. The particle always takes one definite path, but the wave that guides it passes through both slits and creates the interference pattern that determines where the particle is likely to land. This preserves determinism and gives particles definite properties, but at the cost of introducing a wave that is explicitly non-local, that responds to changes anywhere in the universe instantaneously with no signal required. Einstein's locality is gone either way. And then there is the interpretation that makes the most people uncomfortable, including most physicists, which is precisely why it deserves the most careful attention. The relational interpretation, developed by Carlo Rovelli in the 1990s, proposes that quantum states are not absolute. They are relative to observers. A particle does not have a definite state in itself. It has a definite state relative to a specific observer who has interacted with it. Two different observers can have different, mutually consistent descriptions of the same quantum system, and neither description is more fundamental than the other. Reality in this picture is not a single objective state that everyone is looking at from different angles. It is a network of relations, interactions, correlations, exchanges of information, and the universe is what those relations collectively constitute, not things, relations between things. This lands differently depending on what you bring to it. If you have spent time with Buddhist philosophy, with the Madhyamaka tradition's concept of dependent origination, The idea that phenomena do not exist independently but only in relation to other phenomena. The structural resonance is immediate and difficult to dismiss as coincidence. If you have spent time with the process philosophy of Alfred North Whitehead, who argued in the early 20th century that reality is fundamentally composed of events and processes rather than static objects, the same resonance appears. If you have read the philosopher Thomas Nagel's argument that the objective scientific view of the world necessarily leaves something out, specifically the subjective character of experience, the what it is like to be a conscious observer, you begin to see why the measurement problem in quantum mechanics is not just a physics problem, it is a consciousness problem. And this is where the inquiry reaches its most precise and most vertiginous edge. The hard problem of consciousness, a phrase coined by philosopher David Chalmers in 1995, is the problem of explaining why physical processes in the brain give rise to subjective experience at all. Not how the brain processes information, not how it integrates signals and generates behavior. Those are what Chalmers calls the easy problems, not because they are simple, but because they are, in principle, tractable by the standard methods of science. The hard problem is different. It is the problem of why there is something it is like to be you. Why information processing in a physical system is accompanied by felt experience, by the redness of red, the painfulness of pain, the particular quality of this moment as you encounter these words. No physical theory currently explains this, not even in outline. And here is where quantum mechanics and consciousness collide in a way that neither field has fully digested. The physicist John von Neumann, in his 1932 mathematical formalization of quantum mechanics, traced the measurement chain all the way back and concluded that the only place the chain terminates, the only place where an observer that is not itself a quantum system, requiring another observer to collapse it can be found, is in the consciousness of the observer. Von Neumann was not a mystic. He was one of the most formidable mathematical minds of the 20th century, and his chain of reasoning led him to the conclusion that consciousness plays a non-negotiable role in the quantum measurement process. Eugene Wigner, another physicist of comparable stature, extended this into what is now called the Wigner's friend thought experiment, a scenario in which one observer performs a quantum measurement inside a sealed laboratory, and a second observer outside treats the entire laboratory, including the first observer, as a quantum system in superposition. The two observers have irreconcilable descriptions of the same event, and the question of which description is correct has no answer within standard quantum mechanics. In 2019, a version of this experiment was actually performed, not with human observers, but with photons playing the role of the observers, and the results confirmed that the two descriptions are genuinely irreconcilable under the assumption that there is a single observer-independent reality. Either observer independence must be abandoned, or locality must be abandoned, or the measurement outcomes are not absolute facts. One of those three assumptions has to go. All three of them are things your nervous system treats as self-evident features of the world you live in. And yet here we are, standing at the place where the hardest science and the deepest philosophy converge on the same impossible question, approached from completely different directions, arriving at the same border. Physics, following the mathematics wherever it leads, keeps bumping into the observer and finding that the observer cannot be cleanly excised from the description of reality. Philosophy, following the problem of consciousness wherever it leads, keeps bumping into the physical world and finding that subjective experience cannot be cleanly derived from it. Two roads, same border. No one has crossed it yet. But the shape of the border is becoming clearer, and that clarity is itself a kind of knowledge, not the comfortable kind, not the kind that resolves the anxiety of not knowing, but the precise kind, the kind that lets you stop searching in the wrong places, because you can now see exactly where the edge of the known territory is, and what kind of terrain lies beyond it. Here is what that border looks like from the inside. Consciousness is the only thing in the universe that is known directly rather than inferred. Everything else, every particle, every field, every galaxy, every other mind, you know through representation, through signals, instruments, models, inferences. The external world is known indirectly, mediated by the nervous system, filtered through the predictive model, constructed by processes you have no direct access to. But your own experience, The bare fact that there is something happening right now, that awareness is present, that something is being felt. This is not inferred. It is immediate. It is the one thing that cannot be doubted in the way external objects can be doubted, because the act of doubting it is itself an instance of it. Descartes noticed this 4 centuries ago and made it the foundation of his philosophy. What he couldn't do, and what no one has done since, is explain how that immediate, undeniable first-person fact connects to the third-person description of the physical world that science produces, how the firing of neurons becomes the experience of meaning, how electrochemical gradients become the felt sense of recognition, how a physical process becomes the specific quality of this moment. This is not a gap that more neuroscience will automatically fill. It is a conceptual gap, a gap in the framework itself, not in the data. And quantum mechanics, by forcing the observer back into the description of physical reality, rather than allowing the observer to stand outside it as a neutral recorder, has made that conceptual gap impossible to ignore at the level of fundamental physics. The universe doesn't compute you. It might be you, not in the sense that your individual personality is cosmically significant, not in the sense that your preferences shape the laws of physics, but in the precise sense that the category of observer, the thing that quantum mechanics requires but cannot define, may not be separable from the category of experience, that what it means for a measurement to occur may not be fully describable without reference to what it means for something to be experienced. That the hard problem of consciousness and the measurement problem of quantum mechanics may be at their roots the same problem approached from opposite directions. Physicist David Deutsch, philosopher of science and founder of the theory of quantum computation, has argued that explanations, the kind that genuinely account for why things are the way they are, rather than merely predicting that they will be, are the most fundamental things in the universe. Not particles, not fields. Explanations. And explanations require minds capable of generating them. In a universe where explanations are fundamental, the existence of minds capable of explanation is not an accident or a footnote. It is part of the structure. Physicist Lee Smolin has argued that the universe must be understood as a whole, that any theory which treats the observer as external to the universe being described is necessarily incomplete, because the observer is always inside the universe, always part of what is being described, never fully separable from the system under observation. And the physicist John Archibald Wheeler, the same Wheeler who proposed the delayed choice experiment, spent the last decades of his life developing what he called the participatory universe hypothesis, the idea that the universe is not a machine running independently of the observers within it, but a self-excited circuit, brought into being and given definite properties by the acts of observation that occur within it. That the universe, in some sense that he was careful to frame precisely rather than poetically, requires observers in order to exist in the way that it exists, it from bit. Wheeler's compressed formulation, every physical thing, every it, derives its existence from information, from binary choices, from acts of observation that register a yes or a no. Reality, at its most fundamental, is information. And information requires something to carry it, to register it, to make the distinction between yes and no. Something that, so far as we know, only minds do. This doesn't resolve the hard problem. It doesn't explain consciousness. It doesn't prove that the universe is mental rather than physical. What it does is something more precise and more useful. It demonstrates that the clean separation between mind and matter, between observer and observed, between the universe and the thing inside the universe doing the observing, that clean separation, which felt like common sense for 3 centuries of classical physics, is not supported by the most fundamental physical theory we have. The separation was always a convenience, not a discovery. And recognizing it as a convenience rather than a fact changes something, not dramatically, not overnight, but structurally. It changes the kind of questions you are allowed to ask. It opens territory that the classical picture had quietly fenced off, not because the territory was explored and found empty, but because the map didn't include it, and therefore no one looked. The strangest answer, it turns out, might be the oldest one. That the universe is not a collection of things observed by minds that somehow emerged from those things. That the relationship between consciousness and cosmos is not one of container and contained, not one of background and foreground, but something more reciprocal, more entangled, more difficult to speak about precisely, and yet somehow more consistent with the evidence than the tidy alternative that most of us were handed as children and never examined again. It needs a new language. Physics is building one. Philosophy is building one. Slowly, imprecisely at the edges, with more false starts than breakthroughs. But the direction is clear, even when the destination isn't. The universe doesn't compute you. Something stranger is happening. And you have been living inside that stranger thing your entire life, perceiving only the surface of it, because the instruments you were given, biological, cultural, educational, were built for a different set of questions than the ones reality is actually posing. You already knew this. Knowing wasn't enough. Let me speak directly to you now, not to a general audience, not to whoever might be watching, to the specific person who has stayed with this conversation long enough to reach this point, because that person is not watching casually, and we both know it. You have had moments, not mystical moments necessarily, not visions or revelations or experiences that required a spiritual framework to contain them. Ordinary moments, but ones that carried an unusual quality. A moment when the familiar suddenly looked strange, when something you had seen 1,000 times appeared, briefly as if for the first time, and you couldn't quite explain why the familiar version had ever seemed sufficient. A moment when a conversation went somewhere unexpected, and you came away from it, feeling that something in your model of the person, or yourself, had quietly, irreversibly shifted. A moment when a decision felt less like a choice between known options and more like a collapse, an irreversible narrowing, a door closing behind you with a sound you couldn't quite unhear. You have felt the wave function collapse, without that language, without any framework for what was happening, but the phenomenology, the actual felt quality of those moments, is recognizable now that you have the vocabulary for it. The sensation of possibility becoming actuality, of multiple potential futures converging into one experienced present, of something being foreclosed in the act of something else being chosen. You have also felt non-locality, the experience of thinking about someone and having them contact you moments later. The sense in certain conversations that something is being communicated that is not contained in the words, that understanding is arriving faster than the information transfer rate of language should allow. The way grief moves between people in a room without being spoken. The way a shared history creates a field of reference so dense that a single word can carry the weight of years. These experiences have been filed probably under coincidence or intuition or the ineffable, categories that function in everyday life, the way the Copenhagen interpretation functions in physics. They bracket the question rather than answering it. The question is still there. And here is the uncomfortable thing I want to name directly, because this is where the video stops being about physics and becomes about what you do with physics. Knowing this is not enough. Understanding that the observer participates in producing the observed does not automatically change how you observe. Understanding that the predictive model shapes experience does not automatically revise the model. Understanding that coherence is fragile and that premature collapse forecloses possibilities does not automatically make you better at maintaining coherence. The insight and the practice are different things, and the distance between them is exactly the distance between understanding a map and being able to navigate the territory. Most people stop at the map, not from laziness, from a very understandable, very human conflation, the feeling that understanding something deeply is the same as having integrated it, that if the insight is vivid enough, precise enough, emotionally resonant enough, the behavior will follow automatically. That knowledge at sufficient intensity becomes transformation. It doesn't. The quantum system doesn't change its behavior because it has been explained. The wave function doesn't maintain coherence because someone described coherence eloquently. The collapse happens according to its own logic, indifferent to whether the observer has read about it, and the human equivalent is no different. The predictive model runs at speeds that conscious insight cannot match. The collapse of possibility into conclusion happens mostly before deliberate attention arrives. Knowing about it, in the abstract, does not slow it down. What changes it is repeated contact. not understanding repeated as contact repeated, the practice of returning again and again to the moment before the collapse. The discipline of noticing in real time, the instant when open possibility begins narrowing into settled conclusion, and pausing there, not permanently, not indefinitely, but long enough to register that a choice is being made, that something is being foreclosed, that this moment of collapse is not inevitable but is, to some degree, chosen. That practice is not exciting. It does not produce the clean, dramatic shift that insight produces. It produces something slower and more durable, a gradual recalibration of the instrument, a slow expansion of the range of what the predictive model treats as possible, a patient widening of the aperture through which experience is allowed to arrive. You knew this in some form before today. The ideas in this video are not, if you are honest with yourself, entirely new to you. The sense that reality is more porous than the classical picture suggests. The intuition that attention shapes experience in ways that go beyond the obvious. The recurring suspicion that the model you carry is not the territory it claims to represent. These are not ideas this video planted. They are ideas this video gave language to. And language matters. Not because it creates the experience, but because it makes the experience available for examination in a way that unnamed experience is not. You knew this, and knowing wasn't enough, which means the question this video is actually leaving you with is not intellectual. It is practical, not what is real, but how you intend to encounter it now that you can no longer claim you didn't know the encounter was participatory. The secret was never hidden. The aperture was narrowed. We opened this video with a question. Why does the universe hide itself from the people most capable of understanding it? We have earned the answer now, and the answer is this: it doesn't. The universe has not been hiding. It has been operating at every scale according to principles that are fully consistent, fully lawful, fully available to anyone with the instruments to perceive them. The double-slit experiment has been repeatable since 1801. Bell's theorem has been testable since 1964. The mathematical structure of quantum mechanics has been in place since the 1920s and has not failed a single experimental prediction in a century of trying to break it. The information was never withheld. The aperture was narrowed, not by conspiracy, not by failure, by the perfectly reasonable, perfectly understandable process of building a civilization on the tools that worked at the scale where human beings actually live. The scale of objects large enough to see, forces strong enough to feel, timescales short enough to experience directly. Classical physics worked at that scale. It worked so well that it became invisible, not a theory about reality, but the shape of reality itself. The water that the fish of modern culture swim in without noticing it is water. And the narrowing had consequences, not just scientific consequences. Those are being addressed slowly at the frontiers of physics and philosophy. Personal consequences. The unexamined adoption of a classical picture of the self, a fixed entity with stable properties, located in a specific place, causally separate from the world it moves through, whose inner states are private and whose outer circumstances are independent, has produced a very specific kind of confusion. The confusion of people who apply enormous intelligence and effort to navigating a map that does not match the territory, who feel at some level they cannot always articulate that the official description of what a self is and how reality works is missing something, not something mystical, not something that requires abandoning reason, but something precise, something that the most rigorous science in human history has actually found, documented, and then largely failed to communicate to the people whose lives it most directly concerns. That gap is what this video was about. Not quantum physics as a set of facts to memorize, not quantum physics as a metaphor for personal empowerment, quantum physics as a genuine revision of what the word reality refers to, a revision that has been sitting in the scientific literature for a century, waiting for the cultural vocabulary to catch up. Here is the synthesis, in the fewest words that can carry it honestly. The universe is not a collection of fixed objects moving through an independent space, observed by minds that somehow floated free of the physical processes that produce them. It is a network of relations, of interactions, of information exchanges, in which the act of observation is not separate from what is observed, in which separation in space does not guarantee independence, in which the future is not determined until the moment that determination is forced, and in which the thing doing the observing is not a passive recorder, but an active participant in the production of what is real. You are not outside the universe looking in. You are the universe at a particular point of self-examination. And that is not a poetic statement dressed as physics. It is the implication, carefully, reluctantly, rigorously arrived at, of the best physical theory human intelligence has ever constructed, taken seriously rather than bracketed. What changes when you take it seriously? Not everything. Not immediately. The coffee is still hot, the bills are still real, the people you love are still mortal. The quantum revision does not dissolve the texture of daily life into abstraction. What it dissolves is the specific, unexamined certainty that the texture of daily life exhausts what is real. That the classical picture, useful as it is, functional as it is, necessary as it is for navigation, is all there is rather than all your instruments were previously calibrated to detect. The aperture widens, not because the universe changed, because you changed the instrument. And with a wider aperture comes something that is neither peace nor excitement, but something more durable than either, a kind of precision. The precision of someone who knows they are inside a participatory reality, who knows their observation is not neutral, who knows that the possibilities available to them are not exhausted by the possibilities their current model predicts, and who carries that knowledge not as a belief, but as a practice. Not something held intellectually, but something enacted repeatedly in the ordinary moments where the wave function is always, already, on the verge of collapse. The secret was never hidden. The loop we opened at the beginning, why the universe hides itself, closes here with the recognition that hiding was never what was happening. What was happening was that the instruments built for survival were mistaken for instruments built for truth, and the distance between those two projects was never examined because the survival tools worked well enough that the examination never felt urgent. It feels urgent now, not because the world is ending, because you are awake enough at this point in your life to feel the difference between navigating skillfully inside a limited map and actually expanding the map, between managing a fixed reality and participating in a reality that is less fixed than you were led to believe, between knowing what you know and remaining genuinely open to the scale of what you don't. That openness is not innocence. It is not the openness of someone who hasn't yet learned how things tend to go. It is something harder and more valuable, the openness of someone who has learned exactly how things tend to go and has chosen, deliberately, to hold that learning loosely enough that reality can still surprise them. The universe runs on superposition. So, it turns out, can you? One question left open. On purpose. If this conversation moved something, not settled something, moved something, then there is one thing worth doing before you close this tab or put down your phone or return to whatever the rest of your day requires. Not a technique, not a resolution, a question. One you carry into the next ordinary moment you encounter, the next conversation, the next decision, the next moment when your model of how things are begins quietly converting the unfamiliar into the familiar before you have fully encountered it. The question is simply this: am I measuring too soon? Not a judgment, not an instruction to stop making decisions or to suspend all conclusions indefinitely. Just an honest question, asked at the moment when possibility is narrowing into conclusion, when the wave function is on the verge of collapse, a question that creates, if only briefly, the pause that coherence requires. That pause is where everything interesting lives. If you want to go further, into the interpretations of quantum mechanics, into the hard problem of consciousness, into the philosophy of mind that is slowly converging with fundamental physics at this strange and generative border, the next video is already there. The thread continues. These questions do not resolve in a single sitting, and I have no interest in pretending they do. What I am interested in is the person who keeps pulling the thread. If that is you, leave a question in the comments. Not a reaction, a question. The kind you are genuinely sitting with. The kind that doesn't yet have a comfortable answer. Those are the questions that make the next conversation worth having. For both of us. And if only one thing stays with you from everything said here, let it be this. The universe has been waiting for you to stop observing it from the outside. You were never outside.